Hello, good morning, everybody. Thank you for joining us here at Black Hat, and welcome to Breaking Out the AI Cage, Pwning AI Providers with NVIDIA Vulnerabilities. It's my pleasure to introduce Hilay Ben Sasson and Andres Riancho. It's my pleasure to bring on Hilay and Andres.
All right. Hello, everyone. Thank you for coming, and welcome to our talk. It's called Breaking Out of the AI Cage, Pwning AI Providers with NVIDIA Vulnerabilities. And in this talk, we're going to tell you about a vulnerability we found in one of the most fundamental building blocks of AI infrastructure, a library developed by NVIDIA that is so popular, so ubiquitous, that when we found one vulnerability in it, we were able to hack into pretty much every single cloud provider, SaaS provider, every sort of service that you think that offers any AI cloud services was vulnerable to our attack. So we're going to tell you all about this library, this vulnerability we found, what it allowed us to do, and also, more importantly, some of the real-life cloud providers we were able to hack and what we were able to achieve. So we're going to tell you all about that, but just before we do, quick introduction. So hi, my name is Hilay Ben Sasson. Here with me on stage is Andres Riancho. We're based in Israel and Argentina. You can guess which is which. And we work as security researchers as part of the Wiz research team, which means that most of our work relates to cloud security research, researching into platforms like AWS, Azure, GCP, and others. But in the past year or two, we've started delving into this sort of subcategory under cloud vulnerabilities, this emerging new category of AI vulnerability research. During this past year or two, we were able to find issues all throughout the AI research and development pipeline, from issues in data sharing in companies such as Microsoft, to AI services like DeepSeek, all the way to what we talked about in last year's Black Hat, which is AI cloud providers. And after finding these vulnerabilities in many AI cloud services, we've started diving into this new sort of lower layer that powers all these things, which is AI infrastructure, all the open source projects that power the AI cloud. And this is what we're going to talk about today. So this is what we're going to be talking about in this session. We're going to start things off by talking a little bit about what AI infrastructure is, what led us to the idea of doing this research. Then we're going to talk about our research target, which is NVIDIA Container Toolkit, and the vulnerability we found, which allows us to escape every container built with this framework. Then we're going to talk about two of the many real-life case studies where we were able to run this vulnerability on actual cloud providers. And then we're going to sum things up and send you on your way with some takeaways on how to secure AI infrastructure. All right, let's begin. So first things first, let's talk a little bit about what AI infrastructure is, and essentially, how do people run AI? So how do people run AI? Well, in order to run AI workloads and to do AI research and development, you would probably use many of these open source projects that are shown right here. Projects like vector databases like Redis and pgvector, training frameworks like PyTorch and TensorFlow, all the way to inference servers like Ollama, Llama CPP, NVIDIA Triton. So many of these projects right here, we've researched into almost every single one of these frameworks. And in many of them, we were able to find critical remote code execution vulnerabilities, and of course, support them and have them fixed. But after a while of looking at many of these frameworks, we started thinking, what if there's something deeper? What if there's a layer underneath all this that we can also look into? And essentially, what do all these things have in common? So the answer to this question was almost a little obvious when we first thought about it. It's GPUs, and specifically NVIDIA GPUs, because GPUs are pretty much the one common denominator between everything that is AI, between all AI vendors, AI providers, all stages of AI research and development. Everything that relates to AI almost always runs on an NVIDIA GPU. This is the industry standard. So when we thought about this, the first thing we wanted to find out is, because we weren't really familiar with GPUs, is what sort of interfaces does an NVIDIA GPU expose to people that want to work with it? And because we're still security researchers, the more important thing that we wanted to find out is what's the potential attack surface that those GPUs expose to people that work with them. So the short answer to that is a lot. This is a screenshot from the NVIDIA GitHub page. They have almost 600 different open source repositories. And this is just the open source repositories, so really just scratching the surface. So out of all these many different projects that NVIDIA publishes, we started zeroing in on one particular framework which is our research target for today. So without further ado, I'd like to invite to the stage my good friend and colleague, Andres, to talk about our research target, NVIDIA Container Toolkit.
Perfect. So NVIDIA Container Toolkit, what is it and how we hacked it? So NVIDIA Container Toolkit is a container runtime library. It's going to allow you to run AI inference and AI training inside containers. NVIDIA Container Toolkit is going to configure your container in such a way that it allows you to access the GPUs. And it's going to do so by mounting different files, tools, general objects inside of the container. But what happens when you actually start a new container? So if a user wants to use the Docker CLI in order to create a new container, the Docker CLI is going to create an OCI spec. This OCI spec is going to be sent to the NVIDIA Container Runtime, which is a binary that's going to modify the OCI spec to allow AI inference and AI training. The NVIDIA Container Runtime is going to execute runC. runC will initialize, actually, the container, and at some point during that initialization process, runC will invoke the NVIDIA Container Runtime hook. This hook was added by the previous process, the NVIDIA Container Runtime, and is the one that's responsible for actually making the modifications on the container. All of those modifications are the ones that NVIDIA Container Toolkit is responsible for. Once those are done, the process actually starts, your entry point is executed, and your container is ready to run. One of the things that we do when performing container escapes, when trying to do research on containers, is to find and to list all of the mounts inside the container. In this case, what you are seeing in the screenshot is the output of the mount command inside a container that was created with NVIDIA Container Toolkit. As you can see, there is a huge list of different files that were mounted inside the container. In this case, it's interesting for us to notice the userlib path and the different names for the shared objects. But before we do a deep dive into the research, let's understand the basics about mounts. Mounting in the most traditional way is to get a disk into the file system. Once you have mounted the disk, it's accessible, and you can perform actions on that file system. But there are multiple mounts at this point in time with modern Linux operating systems. And the ones that we are going to be focusing on are file mounts or bind mounts. In this case, we're seeing one from the host file system into the container. And this is one of the things that Docker does by default when starting a new container. It's using this in order to configure the host name inside the container. There's a different category of mounts, which is going to be interesting for us because it's associated with our vulnerability, which is mounts from the container to the container. In this case, a resource, a directory, a file is being mounted from a path inside the container to a different path, also inside the container. In this case, the source is the compat directory, and the destination is userlib. And this is interesting because if you go into the NVIDIA Container Toolkit logs, you're going to see exactly that. You're going to see how this software is trying to mount the first path that you see there to the second path, and both are inside the container. This is interesting because we might be able to do something with it. We still don't know what, but it's promising. So what's next? One of the things that we want to do, ideally, is to trick NVIDIA Container Toolkit into mounting the host file system inside the container. And ideally, we are able to do that by creating a specially crafted image. If the image has certain paths and symbolic links and a certain structure, maybe we can achieve that. So let's see how this works. In our first attempt, what we did was to create inside the compat directory a symbolic link pointing to the host file system. And what we expected to happen is that on the mount, we expected to have the host file system in user-lib. We created the Docker file, we built the image, we ran it, we were expecting to see a container escape, and nope, was not working. So we got this path error, which was saying that the live NVIDIA with shared object, which is actually a symbolic link pointing to the host file system, is resolving outside of the container file system. This is a security check that NVIDIA Container Toolkit is actually implementing. And it's interesting because there are a few things that we can learn from it. First, we know that files from the compat directory are actually mounted into user-lib, and the file names are maintained. It's the same file name in compat and in user-lib. We also know that symbolic links are normalized. So based on the previous error, we can say that the symbolic links that are in the compat directory are actually going to be followed, normalized, before performing a mount. So that's good, and it's something that we're going to use during our exploit. And we also know that there is a security control. We still don't know where, but there's something that's preventing our naive exploit from actually working. So our goal at this point is going to be to bypass this security control in order to have the host the host file system mounted inside the container. Let's see how this works. So NVIDIA Container Toolkit is written in C. It's open source, and it has thousands of lines of code. We are not going to show you all of that code now, but we're going to show you the basics in this diagram. Based on our understanding of the code and lots of hours of source code review, we understood that in the first step, what NVIDIA Container Toolkit is doing is it's listing the contents of the compat directory. And it's using a filter in order to get a few files that are interesting for NVIDIA Container Toolkit. This list with live NVIDIA 6 and live NVIDIA 7 are the potential mounts that NVIDIA Container Toolkit is going to process afterwards. In a second step, what it does is to perform the security checks. These security checks are implemented in the do-path-resolve function, which is the one that throws that error that we saw before. So for every potential mount, live NVIDIA 6 and live NVIDIA 7, what the NVIDIA Container Toolkit does is to apply this function. And now we have validated mounts. These validated mounts are then going to be actually mounted. First, it's going to mount live NVIDIA 6. Then, in a second step, it will mount live NVIDIA 7. That's how it works. And maybe some of you are already seeing something strange here. There is a time of check, time of use vulnerability. The time of check happens when NVIDIA Container Toolkit invokes do-path-resolve. So it is applying the security control once and before the mounts are actually executed. The issue is that during the time of use, the mount system call is actually modifying the file system structure. And the security check was applied on top of that file system structure. So the mounts, in some way, and depending on many factors, could actually invalidate the security assertions that you did in the time of check. So that's our vulnerability, and we wrote an exploit for it. Now I'm going to try to explain that amazing exploit that we wrote for the container escape. What we did was to create a specially crafted Docker file with different symbolic links and paths. So the first two things that we have in our exploit are the compat directory and the usr-lib directory. Inside the usr-lib, which is the destination for the mounts, we created a symbolic link. The symbolic link is pointing to the compat directory. Then, inside compat, what we did was to create two different folders, libNVIDIA 6 and libNVIDIA 7. Those folders have different objectives. First objective, making sure that NVIDIA Container Toolkit is going to perform two mounts. Second objective is to bypass the security control. So they are folders. They are not symbolic links. They are going to be, the security check is going to accept both of those entries. So after performing the security checks, NVIDIA Container Toolkit is going to mount libNVIDIA 6. But when it attempts to mount it to the symbolic link, what actually happens is that we override the contents of the compat directory. And because we created another symbolic link with the name libNVIDIA 7, what we're going to see is that on the second mount, the host file system is mounted inside the container. And this is a multi-stage exploit which allows us to get access to the host file system. If you want to see this in a Docker file, this is how it looks like. It's not so complex, most likely because I explained it like step by step. But basically, you create the directories, you create the symbolic links, build that, and then you have your exploit. Your image is the exploit, okay? So let's do a quick summary of the vulnerability. This is a critical container escape vulnerability, which allows us to mount the host file system into the container. And after you do that mount, you have multiple options. You can read configuration files from the host. You can read, potentially, if there are other containers running in the host, you can read the file system for those containers. You can potentially interact with Unix sockets, which exist inside that file system. And there are multiple ways in which you can do privilege escalation based on those accesses. And as I mentioned before, if you control the container image, you win. So many services online allow you to upload the image, and they are going to run it using NVIDIA Container Toolkit. And we're going to learn more about that in a few minutes. But let's see this in action. In this demo, what we're going to be showing is how we run the with malicious image, which has our exploit, using the NVIDIA runtime. And in this case, we create a new container, and there are different things that we can do inside that container. So the first thing is just read etc shadow. It's the one from within the container, nothing special. We can also list the processes. Once again, nothing special, just the processes from my container. But we're going to see that it's possible to access the etc shadow from the host using this weird path, the usr-lib libNVIDIA 8. So if we do a cat of that, we get the etc shadow for the host. So that's Mind-blowing. If you want to clap, now it's the time. Yeah. All right. So after that, once we had access to the file system, we wanted more. We wanted to escalate our privileges inside the host. So we can do that using the Docker sock. The Docker sock is a Unix socket, which you can use to interact with the Docker daemon. And you can use the Docker CLI in order to create a new privileged container. In this case, we are creating a privileged container that also shares the PID and network Linux namespaces with the host. And we create that new privileged container. And we're going to just attempt to list all of the processes. And we're going to see something completely different from before. Because now we have access to all of the processes from the host. At this point in time, we could kill processes, remove files from the file system, from the host. The possibilities are endless, but we are not bad people. We are not going to do that. OK, so this was a dream vulnerability. It was a single vulnerability affecting the entire cloud ecosystem. It was reliable to exploit, so there were no memory addresses, no potential crashes, buffer overflows, or anything like that. Very reliable. So if you had NVIDIA Container Toolkit running on the system, our exploit was going to work, 100%. The risk, critical. We already saw that on our demo. And we were very, very excited about this vulnerability. We really felt that it was a once-in-a-lifetime opportunity to do research. And we were so excited. But actually, it was not a once-in-a-lifetime vulnerability. The WIS research team has an amazing group of hackers. And we found a second critical container escape vulnerability in NVIDIA Container Toolkit, just months after this one. We're not going to be talking about that one here, but maybe if we get accepted to the next Black Hat, we can do that. One of the things that we were discussing while we were researching this vulnerability was how does each vendor going to handle a critical zero-day? From previous research, we know that every vendor, every service is built in a different way, based on the threat modeling that they have done, based on the implementation mistakes that they made along the way. And because of this initial question, we decided to exploit the vulnerability in more than 10 services across different cloud service providers. And we can't really talk about all of those because we don't have time, but let's focus on 2 different case studies. These case studies are representative of what we found in all of the other case studies, all of the research. In order to do that, Eli?
Thank you, Andres. All right. So after we know what the vulnerability is and what it allows us to do, let's talk about its real-life implications to cloud providers out of the many we were able to exploit using this vulnerability. And of course, what sort of impact did we achieve using it? So the first case study is about Replicate, which, for those who aren't familiar, is a very popular AI model gallery service. It allows people to upload their own AI models and AI applications and have people interact with them using Replicate's infrastructure. As you can see in the screenshot, many big AI players are using it to host their AI models, companies like OpenAI, Salesforce, ByteDance, xAI, Google, et cetera, et cetera. So very popular service. So what we wanted to know was, of course, how can we upload our own AI model and have it execute our NVIDIA Container Toolkit exploit? So in order to do that, we had to upload to Replicate in one format only, which is called the COG format, which begs the question, what the hell is a COG format? So COG is the format developed by Replicate, which if you go to the GitHub page for COG, you see that it's described as containers for machine learning. So does that mean that COG is just a fancy name for a Docker container? Essentially, yes. A cog is just a Docker container which runs specific cog code. So we took our NVIDIA Container Toolkit exploit, we added some of the cog code, and the way we built that cog model was actually quite interesting. We built it to act as a shell, which means that when people is us, go to replicate and visit our model, in the prompt input, where you're supposed to put the prompt for the model, we put the ID command, we send it to the model, and the model executes that command and shows that we're running as root. Great, very convenient. So now that we have our own AI model shell, and we have our NVIDIA Container Toolkit exploit running, that means we have access to the host file system. That's great. Now the question is, what's next? So now that we have access to the host file system, we want to try to scan it and try to find interesting files inside. Now the first stop that we had in this particular case was /proc, the procfs file system, which is the Linux file system that shows all the processes running on the host. We wanted to see what sort of things are running on our underlying host machine, if there's anything interesting that pops up. And then, almost immediately, something very interesting popped up. This is one of the processes that was running inside our host machine, and it immediately caught our eye for two reasons. First, it's a password, it's pretty obvious. But the second is actually more interesting. The real reason that this caught our eye is because this password here is a password and an address to a Redis database. And we were actually already familiar with this Redis database from a previous research project that we did with Replicate. This is not the first time that we looked into Replicate. And in the previous time, we were actually able to take over the very same Redis instance. And we were able to prove what this Redis instance does. This Redis instance is being used as a task queue for Replicate, which means that whenever a user goes to Replicate, inserts their own prompt to the AI model, goes to ChatGPT and asks if the sky is blue, that prompt will get inserted to the Redis task queue, and the Redis task queue will bring it forward to the relevant AI model. That can be our own AI model, that can be different AI models. Then it will get the response and return it to the user. Now, the reason that this is interesting is if we take a look at the right side of this diagram, we see that the Redis task queue is connected to all the models. It's connected to our own AI model, but it's also connected to all the other companies' and customers' AI models, which means that this is shared infrastructure. Now, when we did our previous research project and we took over this Redis instance, we were able to prove that this gave us access to all the prompts and all the predictions that exist on the Replicate platform. And it wasn't only the ability to read those prompts and predictions, it was also the ability to interfere with them, meaning that when a user asks a model a question, I could have returned my own malicious answer instead. Now, this is true for both the public models on Replicate and for the private models as well. So when we saw this Redis instance, we already knew how this story ends. We once again have the password. We know what it leads to. So we wanted to try to see if there's any other interesting directions we could take. We noticed that this was running on Kubernetes infrastructure, so we tried to chase that direction, tried to see if there's any interesting lateral movement paths we can do inside the Kubernetes cluster. And as we were looking into that, we encountered a major plot twist in the form of this error message that appeared on our Replicate account, shortly followed by a very nice email from the Replicate security team reaching out to us and basically asking, hey, your activity has alerted some alerts on Replicate's backend. Is this legitimate security research or some threat actor? So of course, at this point, we already knew what our report, what the impact of our vulnerability was. So we stopped everything and reported everything to the Replicate security team. So kudos to them for having some very good alerts. Now let's recap this entire attack flow from start to finish. We started out as attackers deploying our own malicious cog container to our own Replicate pod. Then we ran our NVIDIA Container Escape vulnerability, which gave us access to our own to the underlying Replicate node. That's not our own. It's the underlying Replicate node. That Replicate node disclosed the password to the centralized Redis database, and we know that from this centralized Redis database, we have access to all the prompts and the predictions, the ability to read them, and also the ability to interfere with them. So this was our first case study. Now let's talk about our second one, DigitalOcean. So all of us are familiar with DigitalOcean. I don't think it needs any introduction. One of the many services that DigitalOcean offers is called Paperspace. That's an AI service, allowing, once again, for people to run their own AI models using DigitalOcean's infrastructure. So once again, you already know what's coming next. We wanted to upload our own AI model, have it execute our exploit, and see what happens. So this is what we did. And we ran the exploit, and we now have access to the nodes file system. This is a Kubernetes-based environment, so we have access to the Kubernetes nodes file system. What's next? So we once again want to try to scan it to try to find interesting files inside. This time, because we immediately know that this is Kubernetes, we immediately wanted to see if we have interesting Kubernetes credentials. Because obviously, our own customer pod does not have interesting credentials. But the underlying node might have some might have something interesting, might have an interesting role in the cluster. So do we have any interesting Kubernetes credentials? Yes. This is, as you can see at the top, we accessed the etc Kubernetes directory, not from /etc, but from user lib NVIDIA etc Kubernetes. And in this library existed all the kubelet credentials for the node. Now, we took those credentials and we wanted to see what sort of privileges do we now have. So the first thing that we wanted to take a look at was how many nodes exist inside this cluster. A node, for those who aren't familiar, is a virtual machine, an actual machine. And inside each node, can exist many different customer pods. So we wanted to get some sort of assessment of how big this environment is, how many machines exist inside it. The result for that was over 700. So this immediately told us that this is not our own private environment, and this is shared between us and other customers. So this immediately means that this is an interesting environment. Now that we know that this is not shared, we want to see what sort of privileges do we have inside the cluster. So we did some testing. We did this only on our own secondary accounts. We made multiple accounts because we don't want to access any other customer's data. But on our own secondary accounts, we tried to see what sort of privileges do we have on our customer pod. So we were able to immediately see that we have access to everything inside the pod. We can get access to all the AI models running inside, to all the source code running inside, basically everything that runs on that customer pod. But another thing that we found very interesting was this field called image pool secrets. Because this image pool secrets is a secret that we actually inputted into DigitalOcean when we created our account. It's a secret that's being used to pull the Docker images from our own registry. So we wanted to see, do we have access to those customer secrets? And the answer was, once again, yes. Here in the screenshot, you can see, not really see, it's blurred, but you can believe me. This is my actual Docker image pool secrets. It's a secret that we inputted to DigitalOcean, which gives access to all the images in our own cloud repository to read them, and in some cases, not in our case, but some people configure it like that, also the ability to write those internal images. So, quick recap of this attack from start to finish. We started out as attackers deploying our own malicious container to our own DigitalOcean pod. Using the container escape, we gain access to the underlying DigitalOcean node. And in that node, we get access to those strong Kubernetes credentials. Those credentials allow us to gain access to all of the AI models, all of the source code running on the service, as well as customer secrets, meaning not only access to things that exist inside DigitalOcean's infrastructure, but also the ability for attackers to spread from DigitalOcean to DigitalOcean's customers using those external secrets. So these were our two case studies for today. Two out of the many different cloud providers that were susceptible to this vulnerability. Now, let's sum things up and talk about some of the things that you can take away from this in order to secure your own AI workloads and AI infrastructure. So first thing that we're going to sum up here is in terms of responsible disclosure. Of course, all these issues have been reported to all the respective vendors. The vulnerability itself was assigned this CVE number by NVIDIA, and it was fixed in version 1.16.2, meaning that people upgraded at the latest version are safe. And of course, in addition to the NVIDIA security team, we also worked with the security teams of Replica and DigitalOcean to have them fix their own issues in their own environments. And we're happy to say that those environments are now more secure thanks to our work. So kudos to those teams for collaborating with us. Now let's talk about some of the takeaways that you can take from this research. So first thing that we wanted to take away from it this year is that AI introduces an entirely new software stack to your application. Because we all know what, you all know what your infrastructure for web apps look like, for mobile applications. But when introducing AI as a feature to those things, it comes with an entirely new stack of things like inference servers, training frameworks, vector databases, et cetera. And with this new software stack come new attack vectors, like the one we've seen here today. The second thing that we want to build on top of that is that AI security is first and foremost infrastructure security. Because the bugs we've seen here today, some of them are specific to AI infrastructure, but some of them are just infrastructure bugs. They can happen in AI environments and in non-AI environments alike, which shows the importance of taking care of your infrastructure security, keeping critical dependencies, such as this library, up to date, and collaborating with security researchers, pen testers, red teamers to make sure that your environment is constantly challenged. And the final thing that can be taken away from this here is that containers and containerization should never act as a sole security barrier when separating between environments. Because containerization as a barrier can be broken in many different ways. Things like misconfigurations that we often see in our research, things like kernel vulnerabilities that are becoming more and more common, and of course, logical vulnerabilities like the one we showed here today, which really shows the importance of utilizing stronger barriers like virtualization-based barriers, for example, and also the importance of using safe container technologies like the gvisor in order to make sure that even when you use a container, it's harder to break out of. So these are our takeaways, but before we leave, I want to leave you with one final thought, a teaser, if you will, for the next episode of Whois Research. Because, like Andres briefly mentioned, this vulnerability that we showed you today, we found it several months ago. And of course, it was an entire process of reporting it, coordinated disclosure, until we were able to publicly disclose it to all of you here. But since that vulnerability, and actually just several weeks ago, just a second before Black Hat, we were able to disclose another vulnerability in the same framework, in NVIDIA Container Toolkit, with this CVE number. Now, the thing about this vulnerability is that it's both simpler and more powerful than this vulnerability. This is the way the exploit looks like. You saw the exploit from before, very big screenshot, very big logic of different mounts and symlinks in order to make this work. This is a 3-line exploit. You provide your own arbitrary code, and that code immediately runs outside the container. So my point with this is that this is not a once-in-a-lifetime vulnerability. And it's not a twice-in-a-lifetime vulnerability either. It's an attack vector that can be used to attack cloud providers using one of the most fundamental building blocks, which is the container runtime. So these are the 2 vulnerabilities that we were able to find. The interesting question is, who's the next person that's going to find another interesting vulnerability that allows you to escape from every single cloud provider into their internal infrastructure? Thank you very much.